We're going to apply all of those definitions that we just learned, and we're going to apply them to the graphs of the polynomials, and we'll get a visual. So one of the first things that we covered with polynomials are the characteristics of their graphs, where they are continuous, which means no jumps. They are smooth, no sharp turns. If you look at this graph, there are breaks. So you may not think it's a polynomial, but if I tell you it's a polynomial, that means that we know a couple of things about this graph. When we read from left to right, it looks like it's going straight up, but then we need to connect our graph because it's continuous. There's two ways that we could connect. We could connect down below, but if we do that and we follow it back up, we're looping back in on ourselves. That's not going to work for us. So let's try that again. The only other way we can loop and connect would be to connect up top. Just make a little turn with it. Coming back down, we're going to need to loop over. Then notice that it comes up and then crashes back down. So we can put our arrows at the end. That way we know which way it's headed. All right, so we have our ends. We have the graph completely connected. Let's start to answer some of the questions. First one, is the function even or odd? Notice that my arms are ending the same. They're both going down, which means that we have an even degree. Remember, arms opposite for odd, even degree, they go the same way. Is the leading coefficient positive or negative? How does the right side end? The right side down, like a frown, which means that the leading coefficient is negative. If we were going up, we would have a positive leading coefficient. Finding all zeros of the polynomial. We need to go and find wherever we cross or touch and turn at the x-axis, which I've highlighted here in yellow. So there's our first zero, and that's at -2. Our second zero where we cross or touch and turn, I just circled, that's at 0. And then we continue on to the right, and we have another one at 4. We want to know at which zeros does the function cross the x-axis. And cross literally means that we go from one side to the other. So if we're looking at our graph and we're going from left and right, and we trace it along our first one, we cross from below the x-axis to above at our x equal to -2. When we come down the middle stretch, we're above the x-axis, and then we wind up below the x-axis. We had this little twisty turny thing going on in the middle. So that means at x equal to 0, we're crossing the x-axis. And then tracing it again for the last leg, we come up, we hit, we come back down. So we touch and turn. So we touch and turn at x equal to 4. At what x-intercepts do we have an even multiplicity? Remember, even multiplicity means that we touch and turn. which means that x equal to 4 has even multiplicity. The x-intercepts that have an odd multiplicity are where we cross, which means that at x equal to -2 and x equal to 0, we have odd multiplicity. The last part of this question is find the least possible degree function in factored form that could represent this graph. Okay. We had 3 zeros. We had x equal to 4. We had x equal to -2. We had x equal to 0. And we also said that our leading coefficient was negative. All right, we are going from the answers and working our way backwards. So if we have x equal to 4, that came from the factor x minus 4. If we have x equal to -2, that came from the factor x plus 2. And if you want, we could put the zeros in there, if that'll help, equal to 0, because that shows how we would get from x minus 4 on up to x equal to 4. But if that 0 is just confusing you, go ahead and get rid of it. And here, if you want to move the 0 over, you can for x minus 0. We'll come back to it in a moment. Our leading coefficient we said was negative. Since we're going for the least possible function, you're either going to use +1 or -1. Since we need a negative, we're going to say that a is -1. So let's start building our function. I'm going to name mine f of x. We're going to start with our leading coefficient, which we said was -1. We had x minus 4 as a factor. We have x plus 2 as a factor. And we have x minus 0 as a factor. We'll come back to that at the end. I know that some of you are going, why would I have x minus 0? Now we need to look at the multiplicities. We said that x equal to 4 had an even multiplicity. The smallest even number we know is a 2. For x equal to -2 and x equal to 0, we need to look at the graph. Because they both cross, which means that they're odd. But if you look at these two, I'm going to get rid of all this other stuff so we can see what's going on here. If you look at these two intercepts, we go straight across at x equal to -2, and we take a little bit more time at x equal to 0. Whenever you go straight across, we want the smallest odd number we know, and the smallest odd number we know is a 1. So we are going to use a 1 for our exponent on x plus 2. At x equal to 0, it takes more time to get across. And if it takes more time, that means that k has to be greater than 1. One of the tricks that we learned is that k greater than 1, we start to flatten out near our 0. So instead of 1, we need our next highest odd number, which is 3. Now we can clean this up a little bit. The -1 times the x minus 4 squared is fine. The x plus 2, if you want to leave the 1, you can. But this whole x minus 0 thing is weird. X minus 0 is just x. And then we have our q. And then the mathematician in me really doesn't like just having our x cubed by itself at the end. So I'm just going to move that guy right on up. So we would have -1 x cubed times x minus 4 quantity squared times x plus 2. And again, if you want to include the 1 on the x plus 2, you can. And if you want to get super fancy and drop the 1 and just have the negative, you can do that as well. Completely up to you. But if you keep the 1, that's fine. And there is our function. Let's try another one. We have our function of our polynomials, and we have the graph. We need to connect them if we have jumps, because we have continuous graphs for polynomials. So I'm going to loop wherever there's a break. On my ends, I'm going to go ahead and draw my arrows. Okay. Notice here on the graph, I'm rising left. So rise left, and then we fall right. That's the end behavior of the graph. And that's going to help us determine parts A and B. So is the function even or odd? Since my arms are going in opposite directions, that means that my graph or my function is odd. The leading coefficient, positive or negative. What happens on the right-hand side? Since we fall right or go down on the right, we're ending on a negative, which means that we have a negative leading coefficient. All right, zeros of the function. Remember, zeros of the function are the same thing as roots, solutions, x-intercepts. So I'm going to pay attention on my x-axis. And wherever we cross or touch and turn or do anything to the x-axis, that's going to be a 0. So our first one is a -3. Keep moving to the right. We have a 0 at 1, a 0 at 2, and another one at 4. I'm going to do parts D and E together. We want to know where we cross and where we touch and turn. So what I'm going to do is work from left to right and look at each of the zeros. At x equal -3, I'm crossing because I'm going straight across. I'm going from a positive side of the x-axis and the negative side. So we cross at -3. At 1, we come up and we turn back around. Up and turn around, which means that we are touching and turning at x equal to 1. At x equal to 2, we're crossing. There's a little dip there, but we're crossing. And same thing at the 4. So the only 0 where we're touching and turning is at the 1. Gonna clean this up a little bit. There we go. All right. At what x-intercepts do we have an even multiplicity and which one do we have an odd? Remember, even multiplicity is touch and turn, which means that x equal to 1 has even multiplicity. X-intercepts with an odd multiplicity are where we cross, which means that we have x equal to -3, x equal to 2, x equal to 4. For our least possible degree function in factored form, remember that we had a negative leading coefficient. We have x equal to 1, x equal to negative 3, x equal to 2, and x equal to 4 as our roots. Let's start putting our function together. I'm going to name my function this time g of x. I used f of x last time, and you don't name your children all the same name, so we don't name our functions all the same. We have a negative leading coefficient. Remember, you're going to use 1 or negative 1. And here, since we're negative, I'll use negative 1. X equal to 1 came from the factor x minus 1, because we're moving the 1 back over. X equal to negative 3 came from x plus 3, moving it back over. X equal to 2 came from x minus 2. And move the 4 over to get x minus 4. X equal to 1 was our only even multiplicity. And remember, even multiplicity, we're going to take the smallest even number we know. So we're going to say it is a 2. And then for our odd multiplicities, we need to look at the graph. If it goes straight across, like it does with the negative 3, it's a 1. But with the x equal to 2 and x equal to 4, it takes its time in crossing. There's a little bit of a dip, if you will. It doesn't go straight across. I'm going to zoom in real quick. It's like a little glitch in the matrix at x equals 4. And because they do not go straight across, we're not going to use a 1. We're going to use the next odd number, which is 3. Since we're going for least degree, we're going to use 3. Your exponents will always be 1, 2, or 3 in these problems, because we're going for the smallest. I'm going to clean this up just a little bit. X minus 1, quantity squared. If you want to leave the 1 on the x plus 3, you can. I'm going to get rid of it. And then the x minus 2 cubed, x minus 4 cubed. So all together. And again, if you want to get rid of the negative 1 out front and just put a negative, you can. But when I do that, I tend to drop my signs, and you know that's never good in math. We have one more, just because I know that some of you need or want additional help and practice. So first thing first, connect with any jumps, and then I'm going to put my arrows on my endpoints. Here, since my arrows are going the same way, notice that we are rising left and rising right. Since we're rising left and rising right, our arms are the same. And if our arms are the same, we have an even degree. Leading coefficient, positive or negative? What's happening on the right side? How do we end? The right side is positive because we're rising, which means that our leading coefficient is positive. Looking at our zeros going along the x-axis, The first one we hit is -3. Then we have 0 and 1. At which zeros does the function cross, and which one do we touch and turn? I'm going to go through and look at these from left to right. So I'm going to do parts D and E together. Notice that we come down, we touch, and we turn at -3. So touch and turn at -3. We're going to touch and turn at 0. We touch and turn again at 1, which means that we do not have any x-intercepts where we cross. So I'm going to write D and E does not exist. Remember, even multiplicity means that we touch and turn. So we're going to have all of our zeros, our x-intercepts, our roots, our solutions for touch and turn, but we're going to have none for our crossing with the odd multiplicity. So D and E, or none if you want. Last part, we need to write our functions in factored form that could represent the graph. Remember, we had a positive leading coefficient. Then we had x equal to -3, x equal to 0, and x equal to 1 as our zeros. This time I'm going to name our function h of x. We have a positive 1 on the leading coefficient. Remember, we're always going to use 1 or -1. The x equal to -3 came from x plus 3. You can do x minus 0 if you would like. If you already know where we're headed with that, you can skip the x minus 0 step. And then we have x minus 1. Let's go ahead and put in some exponents. For our exponents, they are all even. And the smallest even number we know is 2. So we're going to have them all with squares. Let's clean this up a little bit. We would have 1 times x plus 3 quantity squared. X minus 0 is just x. And x minus 1 squared. We don't really put the parentheses around the x with the x squared because there's nothing in there. We don't need the parentheses. But here it looks weird to have the x squared in the middle. So I'm going to bring it out front because we can change the order of the multiplication. 3 times 4 is the same thing as 4 times 3. And then finally, if you don't want to write the leading coefficient of 1, you don't have to. We can write this as x squared times x minus 3, x plus 3 squared times x minus 1 squared. Any of these versions for the last 3, well, even the last 4, I should say, are the same. It's just the very last one we did is the prettiest one version for our math.